Hello everyone, this is yours Peels of 3dprint.com with another edition of 3D Printing News Unpeeled. Today, our roundup of additive manufacturing and 3D printing news for the day includes Chromatic 3D printing materials, which has released a smooth mode for extra smooth parts. So Chromatic is a company that uses a mixing nozzle when they mix liquid elastomers, which are then subsequently cured after being mixed in the nozzle. This is very similar to like a Viscotech nozzle where you can mix and dose particular materials. But in this case, what they're doing is they're combining this with a thermostat elastomer and a curing step. So in this case, what they've done now is they've essentially developed a new feature, new processing technology that allows them to make very, very smooth polyurethane parts. And these parts can be made without post-processing. So directly out of the printer, they're incredibly smooth, as you can see. Chromatic 3D printing materials, 3D materials is a relatively unknown startup, but they're doing some work that might be very breakthrough in some very, very specific areas. So if you can see on these tiny components here, these could be, incredibly exciting components for some use cases. Now, another component, which I'm not entirely sure if it's being made with smooth mode, but it definitely is being made with their technology, will show you what you can do by using their materials in their process. So what we can do is make rubber-like air-filled components. So we can make seals, gaskets, bellows, bladders, or we can also make kind of harder kind of items like bushings, and we can customize these things. This would be very advantageous for example, soft robotics, but also sports equipment, but also things like machine building, where you might need really specific kind of fasteners or rubberized components, and that could take you a long time to make otherwise. What you can also do is technologies print directly onto textile. And I absolutely love the idea of making custom air insoles, so custom variable density insoles with custom air components at particular locations. For you, that would be very different than for me, because I would have, for example, more air on my toes because I walk much more on my toes. You would have more reinforcement there, maybe a little less air, but then more air, protecting your high instep, for example. So that kind of thing I really love about this technology. I love the possibilities in that area. And also just soft robotics, we have very few applications for that, but that could be a very fruitful area as well. It's ideal for things like where you need a smooth mating surface, you need things to be airtight and watertight. They can do Shore A50 to A90, and you can have even custom flexibility. And if you can see here, these are some of the technical data of some of their materials. I have many more. You get different shore hardnesses. The MPAs to me look, the strengths, to me look very impressive. And the elongations as well. And you could really see that there could be really specific applications. This could be a real endpoint for people where they get stuck in 3D printing and have this really incredibly specific application that can't be done. And it's easy how this could really fill that niche. The next is SEAM. SEAM is a technology developed at one point by Fraunhofer IWU, and I knew it existed. I didn't know this was commercially available to partners, let's say. And I think this is a fundamentally very breakthrough technology in the fact that it's a refinement upon some ideas that we've seen before, but is doing this in a way that makes it very applicable. What the Fraunhofer people have done with the screw extrusion additive manufacturing is a couple of things that really solve a lot of problems. So first off, the head is stationary. The platform is a hexapod platform underneath. Now, hexapod platforms are the similar kind of air-bearing type platforms have been used. They're quite expensive as motion stages go, but they've been used very extensively in high reliability applications of a lot of things. What that allows you to do is you're actually moving the build platform through this 6-axis hexapod. And that gives you an incredibly high amount of design freedom. What they've done on top of this is they've had a screw-based extrusion of pellets, which of course lowers the cost and makes it very precise to extrude the right material at the right time. And of course, by using pellets or by using granulate, you're significantly reducing your cost of the 3D printing material. That could be as much as a factor 10 or a factor 100, depending on if you pay depending on what material it is. They can extrude up to 100 grams to 10 kilograms an hour. They can use materials up to 400 C, and they say that they're about 8 times faster than FDM. Of course, it would depend on the part and a lot of different geometries. But this, for you making a large series of plastic components, is, I think, a super exciting technology. It's also relatively large scale. Also, a lot of this is opened, by the way, and a lot of this is because of the movement of this hexapod, which needs quite a bit of room to move. What they've also done is to marry the screw with a kind of a dosage unit higher up in the extrusion chain, let's say, and this means that they can kind of do skywriting essentially, but then for FDM they can try to change the amount of material that is deposited, that just flows at a particular time in the design, so they can slow down material feeding per corner or something like that. So I think that's a brilliant move generally. This exists previously, but I think this is ripe for exploitation. For these kind of things, really, it would really depend on the specific geometry that really makes sense for this. But I love that people are just looking beyond polar or beyond just regular gantry-based printing into some technologies. If we look here, the parts that they're making so far are quite large. And this could be an area where, of course, regular FDM or FFF or material extrusion, whatever you want to call it, today is not cost effective, or is way too slow to make the machine utilization quite horrible. One of the things that they've worked on together with KTM, they worked on like a sports seat. One could imagine this kind of customized large scale applications could be very difficult to do with other materials. I really think the right person with the right application has to come along to where this would really make sense. But if it makes sense, such a technology would be an incredibly exciting one. The next news item you've probably already seen before. It passed a lot of people's news feeds yesterday. It's an aerial additive manufacturing technology. I think this is going to make a lot more news as well. It's a series of autonomous robots working together like a swarm, where a scan drone will scan an object to do kind of quality assurance on the fly, see where things have built and where things are to be built. And then various build drones will come in and leave and deposit materials at various areas. This comes from Katao Zhang and a whole bunch of other people. The team involved in this was immense. And it comes from Imperial College London and a whole bunch of other different institutes as well. It was published in Nature. And of course, the path planning and this kind of thing ought to be incredibly difficult. In addition to this path planning and the scanning, directing the drones to build where necessary, they also have a kind of self-writing nozzle to make that print process a little bit easier. They made a kind of cementitious polymer mix to make this possible. Now, if we look at this as a build technology, we're going to see a lot of problems. Like the cost is going to be immense. The amount of material you can carry is going to be quite difficult. The structure itself does not look great. But think about, building in very, very remote locations, building a foundation for something you're going to put in later, in a military context. Something like this is going to make sense very quickly. I also like this very much for farming, much more than building certain structures outside. Imagine building a structure in a really remote place to collect water, for example, or a structure to make shade somewhere, or a structure to take a desert and turn that desert into kind of like a rewilding this or regrowing the desert. Imagine this autonomous drone, would also then have solar panels and just keep building structures out there to create shade or to protect pods. That kind of a thing, to me, is a wonderful application for this. It's something where you just dump the series of swarm of drones out there to just autonomously regrow a desert and replant it as well afterwards. I like that kind of thing. I'm not sure if we're going to be building a lot of stuff in attainable, non-denied areas, but I do think this is an application. We saw a couple of weeks ago already and autonomous kind of build robots, work swarming together to build a dam. And these kind of visions are going to become more commonplace. I really like the idea of having autonomous vehicles, autonomous tracked vehicles to build objects together autonomously as well. So we're going to see a lot more of this in papers and in patents. Are we going to see a lot more of this on the ground actually making sense? Well, I think in the military, maybe some oil and gas. I think in these kind of remote farming things, remote water harvesting, I think this is, going to be the real area there. So CSEM, which is a research institute, and CERN, and Thales, and a couple of other partners are going to be making smart pipes. And smart pipes is a it's a kind of vision statement thing for a lot of stuff that's happening already. And these smart pipes are going to play roles, hopefully, in the future of CERN itself, the particle accelerator itself, the space station, space applications, and beyond. The idea is to enhance thermal control by making 3D printed pipes using embedded sensors. Now, the first thing I thought when I saw this is this is the absolute and most incredible kind of application for Fabrasonic, working together with other technologies like Hollow AM and stuff like this. It's not really sure what they're going to be using. It looks like different technologies. But this is a wonderful idea anyway. This is part of a HEAD, which is a part of one of the CERN-managed projects, which combines Switzerland, CERN, and a bunch of EU research initiatives with some Horizon 2020 money from our friends, the EU. So the idea is thermal control is really important. Thermal control devices are really complex, and they need a lot of wiring. That brings with it a lot of weight. How about we make a much more integrated, much more lightweight, much more exciting thing? What they're doing specifically here is to embed the sensor in the pipe, within the pipe, inside of it, right? And then to have an energy recovery device on top of that that powers these embedded electronics and enables wireless data transfer. So you would have like some kind of Stirling engine kind of thing, some kind of heat recovery thing on this, so that the heat traveling through the pipe is not only monitored, but also it actually powers this device. So you can scan it, it can read out its own thing, and it can maybe even in a future iteration kind of change some settings and stuff like that. The idea in the future is to use this as a springboard to integrate 3D printing and integrate these sensors into a lot of devices. This, of course, fits really, really well into the EU kind of digital twin, Industry 4.0, kind of making industry more efficient, making industry smarter kind of approach that the EU has been doing. And it also fits into this whole vision of the sensors everywhere, digital twin, IoT kind of vision. 3D printing, I think, is a logical process. I hope they look at processes in combination, right? So imagine here you'd use the sensor, you'd use maybe Nano Dimension for part of it, you'd use aerosol jet for different components, you'd FDM for the housing, making that planar FDM to make that conformal to a pipe, for example. And you use binder jet for the heat plate, and then powder bed fusion for some complex heat sinking. Like that, to me, is the vision that really makes sense to really make these technologies optimally work together. I hope they do this. And I hope they spend this $2 million project well. I think it's a wonderful idea, and I think in aviation and space travel, satellites, this kind of thing will really be able to help predictive maintenance and will help extend the life of things and reduce service intervals, and maybe even optimize devices where we can track just how much heat is being expended in what kind of situation. And the next generation of satellite will be much more efficient because we exactly know what conditions cause what heat transfer and build up and stuff like that. And I love the idea of just heat recovery, like Stirling engines and stuff, really populating devices to make them more, better functioning overall. So this was another edition of 3D Printing News Unpeeled. My name is Joris Peels, and I hope you really enjoyed this. This was brought to you by 3dprint.com.